If it hadn't been discovered when it was in 1901, no one would possibly believe that it could exist because it's so sophisticated.
This mechanism would be remarkable even if it was a less clever thing than it is.
This is the story of one of the most extraordinary finds in history. This corroded bronze object is a machine that can look into the future. It was built 2,000 years ago in ancient Greece.
Somebody somewhere in ancient Greece built an extraordinary machine that was actually a mechanical computer.
100 years ago, a group of divers chanced upon a wreck full of the largest hoard of ancient Greek treasures ever found. Among the priceless ancient Greek bronze sculptures is another bronze object, no bigger than a modern laptop. It's known as the Antikythera mechanism. As a team of scientists try to unravel the secrets of the Antikythera mechanism, we are taken on a journey that charts the fall of one great ancient empire and the rise of another.
An ancient Greek scientist had done a truly remarkable thing. He'd found a way of using bronze gear wheels to track the complex movements of the moon and probably all the planets as well. It was a mechanism of truly staggering genius.
This is the story of the world's first computer. If it hadn't been for a storm on the rocky Greek island of Antikythera 100 years ago, one of the most bewilderingly complex objects ever to emerge from the ancient world might never have been found. After they'd sheltered from the storm, a team of sponge divers decided to try their luck underwater. The sponge diver hadn't discovered a graveyard. He'd come upon a heap of marble and bronze sculptures. It was part of the biggest hoard of Greek treasure ever found. It had come from an overloaded Roman galley sunk 2,000 years ago, as Rome's empire began to grab Greece's overseas colonies in the Mediterranean. By accident, the divers had rescued some of ancient Greece's most beautiful artifacts. But among the bronze and marble statues was perhaps the most important object of all, item 15,087 in the Athens Museum. It had soon split into several badly corroded lumps of bronze. Then, remarkably, researchers noticed tiny gear wheels in the machine. Much later, the Antikythera mechanism, to the amazement of scientists, would be revealed as the world's first computer, built 2,000 years ago by a Greek genius.
You're just amazed by the quality of the workmanship, and then suddenly you look and you see that they're tiny Greek characters engraved into the actual metal itself. The shock they must have had when they first saw this and saw these gear wheels. They knew wooden gear wheels were used in Greek mills and so on, but nothing was known like these precision metal engineered gears.
It was against the background of this Greek mystery that in the year 2000, a team of international scientists was formed by astronomer Professor Mike Edmonds to investigate the puzzle. As a group, they were an odd mixture of astronomers, historians of science, and mathematicians.
The Antikythera mechanism is an incredible puzzle. Probably one of the most fiendish puzzles in history. We had no confidence ourselves that we would actually be able to solve it.
Tony Freeth, a mathematician, coordinated and led some of the team's major investigations.
So when we started, we thought we'd try and put the basic information together. Maybe the objects from the wreck could help us piece together some clues. You know, how old was it? Where did it come from? We had many, many questions.
In 1976, another expedition to the Antikythera wreck by the famous French diver Jacques Cousteau had given them their first clues. Cousteau discovered much cargo left after the initial find in 1900. There was more pottery, many more amphorae, some of the original timbers from the ship, and bronze figurines. Cousteau believed it was a Roman galley. Significantly, his divers brought up bronze and silver coins, an archaeologist's dream for dating a treasure site.
These are the coins that came from the expedition of Jacques Cousteau in 1976?
Yes, a lot of silver and bronze coins.
So 36 silver coins plus some bronze coins.
Some bronze coins.
Okay, so this has a basket on it.
It has a basket introduced by the kings of Pergamon. Most of the coins were struck in Pergamon, around, let's say, 30 of them, and the rest were struck in Ephesus.
But what do you think they actually tell us about where the ship came from?
They can tell us that the ship came from Asia Minor.
What date would this be?
And these are dated in the decade from 70 to 60 before Christ.
These coins from the cargo had given us our first clues to the likely date and route of the ship's last voyage.
So what were these Greek treasures and the strange Antikythera mechanism doing on a Roman ship 2,000 years ago?
Since the time of Homer, the Greeks had been great sailors, forging settlements and remote colonies in places such as Pergamon in Asia Minor and further north in the Black Sea. And everywhere the Greeks went, they left giant temples to the gods that protected them. But by the time the galley sank in the middle of the 1st century BC, these far-flung Greek settlements had become vulnerable to a hostile new power in the Mediterranean, Rome.
But as we looked closer at the Antikythera cargo, we began to realize this wasn't a marauding Roman warship plundering Greek colonies, but something more unusual.
It was a quite big ship, probably a huge big for this period, for these Roman times. One of the probably biggest trade ships. Only few harbors can receive this kind of ship, and that is probably Delos, Pergamum and Ephesus, that region, Rhodes.
Tell me about where these amphorae come from.
Look, these amphoras, these 5 amphoras, they're coming from Rhodes, from the island of Rhodes. These 2 of them, they're coming from the island of Kos. They were containing wine.
Tell me what you can say about the date of these amphorae and therefore the date of the shipwreck.
These amphoras, they are between 65 and 50 BC.
These dates were almost identical to those we'd found on the coins from the wreck.
So we believe that the galley started its journey somewhere in the Greek colonies in Asia Minor. Possibly Pergamon, possibly Ephesus, but somewhere along this coast. The ship would have sailed down, probably calling in at Kos, then onto Rhodes, where it loaded more amphorae, and then set out, heavily overloaded, on the trade route back to Rome, where it met its fate in a storm at the island of Antikythera.
Some of the ship's cargo had been dated very accurately to between 70 BC and 50 BC. Perhaps this was now close to the vessel's last voyage. But the group couldn't be entirely sure the bronze mechanism really was 2,000 years old. Perhaps it was a modern machine that had been dropped from a passing ship, by chance coming to rest on the wreck the sponge divers had found. So the team decided to scrutinize previous work done on the machine.
The team were drawn to the work of Derek de Solla Price, he was an English-born physicist. He started work in the 1950s, first in Cambridge and later in Yale. He was the first to really examine the pieces in very great detail, and he started doing radiographs and being able to see the insides of the mechanism. Suddenly, out of those radiographs, they realized there were 27 gears inside this thing. It was seriously complicated.
Price was the first person to count the gear teeth with
Yes.
Caracalos and
And
Caracalos'
his
wife
wife,
as well.
Emily.
Yes, yes.
And they did it by drawing around the gears and literally just counting it. So it wasn't surprising they didn't get entirely accurate all the time.
But all the two-dimensional X-rays of the gears were overlapping, making this task formidable. Price realized if he could find the exact tooth count on a gear wheel, it might begin to unlock the mechanism.
So Price had identified a 127-tooth gear in the X-rays of the mechanism.
He also had the number 235. And these two numbers are very important in ancient Greek astronomy.
Price wondered whether an ancient astronomer might be using the 127 gear wheel to follow the movement of the moon. This was a revolutionary idea.
Price was beginning to have sleepless nights worrying about the authenticity of the mechanism. If the ancient Greek scientists could produce these gear systems 2,000 years ago, the whole history of Western technology would have to be rewritten.
The team believed such sophistication was surely beyond the great achievements the ancient Greeks had made more than 2 millennia earlier. They are regarded as some of the most creative people the world has ever known. 2,500 years ago, they began a revolution in thinking, followed by technical advances comparable to those of the Industrial Revolution. This peaked in the 5th century BC, when Athens, the largest city-state, produced magnificent art and architecture that is still revered today. In 9 years, they built the huge temple of the Parthenon to their goddess Athena on the sacred Acropolis rock that dominates Athens. Public discussion of ideas and oratory led to larger public events like theatre. This huge theatre at Epidavros could hold 14,000 spectators, and it had superb acoustics. Drop a coin on the stage and it could be heard in the back row. The ancient Greeks developed astronomy, which they treated as a branch of mathematics. They were able to plot how heavenly bodies moved in space and calculate their distances and know the geometry of their orbits. Now, with the mysterious gear wheels, the team suspected ancient astronomers were trying to mechanize the movements of the sun, moon, and planets. Could they put astronomy and complex mathematics into a device and program it to follow the motion of their closest neighbor, the moon?
The phases of the moon were a fact of central importance for the ancient Greeks, to plan ceremonies such as the ones that were held in the Parthenon up on the rock above me.
The number 235 that Price had found was the mechanism's key to computing the cycles of the moon.
The Greeks knew that from one new moon to the next was a time averaging about 29.5 days. But that made a problem for their calendar if they were going to have 12 months in every year, because 12 times 29.5 makes only 354 days, 11 days short of the solar year, the natural year. So the natural year with its seasons and the calendar year would quickly go out of sync. But the Greeks also knew that 19 solar years almost exactly equals 235 lunar months. That means that if you have a cycle of 19 calendar years, then your calendar is in the long term going to stay perfectly in line with the seasons. Through Price, the mechanism was beginning to yield one of its secrets.
And on the back of the mechanism was the remains of an upper dial with Price's 235 divisions representing the 19-year cycle. The Greeks called it the Metonic calendar. Why had these ancient astronomical numbers and a dial been built into the machine? The phases of the moon were immensely useful to the ancients. These told them when to plant crops, when to fight battles, the timing of their religious festivals, and whether to travel at night.
The 127-tooth gear had given Price a clue to another one of its functions. The ancient Greek astronomers realized that while it takes about 29.5 days for the moon to catch up again with the sun, it takes only 27 1/3 days for it to get back to the same star in the sky. So that's the length of time it takes for the moon to go once round the Earth. If you do the arithmetic, what you find is that in that 19-year cycle, this means that there are 254 orbits of the moon around the Earth. But that's a lot of teeth to put on a small gear. So what the designer did instead was to take half of that number. Half of 254 is 127, and then used other gears to multiply its effect up to 254. Price had discovered the 127-tooth gear, one of the other main functions of the mechanism, a display of the moon's revolutions around the Earth.
We now had two prime numbers, 19 and 127, which both had crucial functions. Were there more? After 20 years of intense research, Derek Price thought he'd solved the puzzle of the mechanism. But he hadn't used up all the gears, particularly a large gear at the back, which he thought had 222 or 223 teeth. So we became sure that Derek Price hadn't solved the puzzle of the mechanism. We were desperate to see inside the Antikythera mechanism. One day I was looking at a science journal and I saw this exquisite X-ray picture of a goldfish. Another picture I saw was of a locust with all this fine detail of the internal structure. Could we use these techniques to look inside the fragments in 3 dimensions?
Tony Freeth took a chance. He phoned a UK company who are world experts in X-ray technology. Could he convince them of the importance of the mechanism?
Well, to begin with, I wasn't interested. My colleagues told me it was some ancient bronze calcified lump. So really, I determined to ring up Dr. Freeth and say, I'm really sorry, but we're unable to do this because we haven't got a system powerful enough to penetrate the sample. But after an hour's conversation, I was pretty much convinced that this was something we had to do.
Roger decided to build a special prototype machine for us to X-ray the Antikythera mechanism. It was an extraordinary decision.
The financial director was absolutely furious. He stormed out of our meeting, declaring I was going to bankrupt the company.
The Antikythera mechanism is extremely fragile. So Roger agreed to take this machine, this 8-ton machine, to Athens to study the fragments. When they got to Athens, the police cleared the streets so that we could get the lorry through. It was an X-ray machine the size of a small van, basically, but weighing 8 tons. With the help of 3 forklift trucks, we managed to shoehorn the X-ray machine through the entrance into the basement of the museum. You could describe it as a very high-tech machine to crack one of the deepest and most extraordinary conundrums that have come from the ancient world. This thing is remarkable beyond belief. The Antikythera mechanism itself is extremely fragile, and since it was brought here more than 100 years ago, it's never moved from this museum.
We need to go this way.
So we had to bring the technology to the mechanism rather than take the mechanism to the technology. We'd made this huge team effort. We arrived there with the machine without any confidence that we would find out anything new. And the way that the technique works is that you put a fragment on a turntable and you rotate the fragment in front of the detector and take maybe 3,000 different X-ray projections. A computer then puts this all together, so you've got 3D X-rays. And when we saw the first image of fragment A, it was absolutely amazing. It was like a new world, really. It's almost like going to an unknown underwater world. Now we actually had the data to enable us to really tackle this problem of how it worked for the first time. I decided to make a digital model of the Antikythera mechanism in order to try and understand better how it worked. What's remarkable is how much is crammed into such a small space in the main fragment. All the gears are packed together in layers, almost touching each other. We found 27 gears. Probably in the complete mechanism, there were 50 or 60 gears. It upsets all our ideas about what the ancient Greeks were capable of. It rewrites the history of technology. It tells us that things were going on in 2nd century BC Greece, which we had no idea about. Would our new data from the X-rays solve the puzzle of the largest gear wheel? It was broken and had either 222 or 223 teeth. 223 was another prime number. The two prime numbers we already knew about were 19 and 127 in the gear that Price had found. Our plan was to follow this trail of prime numbers to see if they would unlock the astronomical secrets of the mechanism.
But all this time, the international research team had a rival. Michael Wright had been working in London on the riddle of the mechanism for 25 years.
And slowly you get the metal to work round the instrument till it gets nearly symmetrical. Then you can put it on there. Where it's tight, you...
Michael Wright makes things, from musical instruments to a working model of the Antikythera mechanism. He was formerly an expert on engineering at the Science Museum in London. Previous research showed the bronze fragments with their gear wheels had once been fitted into a wooden box that hadn't survived. So Wright had built his multi-geared machine into a box powered by a handle on the side. Michael Wright's own model included a radical addition to that of the international teams. Using earlier ideas by Price, he built a very complex and highly ingenious planetarium on the front of his mechanism.
It's very obvious there's a lot of mechanism lost from the front of this, which is the big fragment. There was a pattern of pillars on this wheel. It had structure, some sort of structure that revolved like a merry-go-round. And what I ended up with was models of the planets. This is a model of the Greek cosmos, geocentric. You can think of this cover plate in the middle as representing the Earth, and everything goes round it. The easy one to spot is the moon, because that's the fastest moving thing on the dial, and it's the front pointer. The night sky was the ancient Greeks' television. What else were you going to look at night? People were much, much more aware of the sky. The calendar was organized according to the moon. Official positions changed. Debts became payable on the new moon. You had to have a calendar that in some way reconciled the year controlled by the sun with the month controlled by the moon. They're tricky numbers, and they're built into the model.
These numbers had to be translated into gear wheels with awkward teeth counts like 53 and 127. How did the ancient engineers do this? Michael Wright had the simple answer.
There's nothing difficult about any number. 53 is no harder than 54. We think that the Greek mechanic started with a prepared sheet of metal. He didn't have a hacksaw, so he had to cut it out with a hammer and chisel. What I usually do for almost any number is to divide the wheel into 6 to begin with by stepping the radius round. Now, I ought to be fitting 8 and a large fraction into each of those 6 divisions. So now I'm going to attack it with a file and make teeth. That's 53 teeth. That's ready to go into my Antikythera mechanism. I suppose my Hellenistic workman friend would have taken about half an hour to make that.
Meanwhile, as Tony Freeth created his own digital model, he was suspicious of Wright's use of gear wheels with odd numbers like 53 teeth.
53 teeth. Why 53 teeth? It seemed to have no function. Odd prime number, no function. And I thought 54 was a much more likely number. You know, divisible by 2, divisible by 3 several times. So in my model, I changed Wright's 53 to 54. And it proved to be a huge mistake.
This tiny change would escalate into a major problem in the future. But there was a more pressing problem. None of the investigators working on the machine had ever been able to explain the function of the large wheel, the one with either 222 or 223 teeth at the back of the mechanism.
We were desperate for more data. We knew that the surfaces of many of the fragments were covered in inscriptions, which were incredibly hard to read. And then I read about this technique invented by a guy called Tom Maltzbender at Hewlett-Packard. It's a brilliant technique for enhancing the surfaces, surface details. One of the ways this technique had been used is on paintings, for example, at the National Gallery in London, to look at the surfaces of paintings and just looking at brush strokes, the fingerprints, the essential form. And this can reveal things that are under the surface. Here, for example, is a painting by Frans Hals. And if I move the virtual light, I can see the brush strokes on the painting. I can see how the painter's applied all the brush strokes. And we thought this would be an absolutely brilliant technique to use on the Antikythera inscriptions. I got on very well with Tom, and I then set about persuading him to come to Athens to use his technique on the Antikythera mechanism. Tom had an absolutely brilliant insight, which is that you can look at a surface by taking a series of still photographs, 2D still photographs, with lighting from 50 different angles. Flashlights arranged in a dome, flash, and a picture's taken with the light at all these different angles. And this means that a computer can put all this information together, and it can take away all the confusions of the surface coloration and the surface texturing, and show you the essential form of the surface. This is beautiful. You can actually look in detail at an inscription, say, and the clarity of the image leaps out at you.
Both this technique and the X-rays proved invaluable in reading the inscriptions.
These inscriptions were very tiny, maximum a couple of millimeters high. I was working overnight in front of my computer and trying to transcribe what I was seeing. The letters appeared like ghosts within the fragments. Lambda 230, Epsilon 235, spiral sections 235. Should be the 19 years calendar. One particular night, I've discovered a completely unknown layer of text. I tilted a little bit the angle, and a whole new layer of inscription appeared. My heart was beating, and suddenly I started reading mechanical words about gears. The word gear appeared for the first time, like a kind of a user manual. This was totally unexpected.
And new data from the inscriptions was producing another significant breakthrough.
Sigma Kappa Gamma. it is there.
What is there? How much is
223.
there? 223 is there?
Yes. The line below.
Definitely 223.
Yes, 223.
Did this mean the large gear wheel at the back of the mechanism actually had 223 teeth? If so, what was its function? Then, with a chance discovery in the museum, the mystery began to unravel.
I went to the stores of the bronze collections and I started looking the places where the Antikythera were. So I found this tray and with 8 boxes, and then I was looking around and I've seen some other small fragments in the boxes. Altogether we have 82 fragments.
One of the new fragments in particular stood out. Mary had labelled it as Fragment F, but it also appeared to contain part of a curved dial.
Measuring only a few centimetres, Fragment F would turn out to be the key to the big wheel and the entire mechanism. A couple of weeks later, Tony Freeth started to examine the 3D X-rays taken of Fragment F.
I suddenly realised with mounting excitement that Fragment F formed a new scale on the lower back dial of the mechanism. In order to understand this new 4-turn spiral dial, I wanted to count the scale divisions round the whole dial, make an estimate of them. So I started to enter all the data into an advanced computer program, and the results seemed to come out as 220 to 225. So I became sure that it must be the magic number 223. We found the importance of the number 223 at the British Museum in London. 3 centuries before the golden age of Athens, around 700 BC, Babylonian astronomers had made the breakthrough. Over hundreds of years, they'd written thousands of astronomical tablets, many recording the huge significance of the number 223. The Babylonians called it the 18-year period. John, tell me what all these tablets are here.
We have maybe 3,000 or 4,000 astronomical tablets, ranging from reports sent to the king by scholars advising him on astronomical matters to how to interpret omens and what this meant for his kingship.
Tell me about the 18-year period.
So the 18-year period describes a cycle of 223 months used to predict eclipses. So this is what we would today call the Saros cycle. By looking at past observations, they saw that after 223 months in the 18-year cycle, eclipses of the same kind, say lunar eclipses, would repeat with very similar appearances.
Tell me, John, how the kings of Babylon reacted to an eclipse prediction.
A substitute, usually a criminal or someone like that, would be officially appointed to the throne and the real king would officially abdicate. So this is an example of one of the tablets that, again, is a letter describing this substitute king ritual. It mentions down here that the substitute king ascended the throne and took these bad omens, these signs, onto himself. Once they were deemed to have done their worst, the substitute king would be killed and the real king would come back to the throne unharmed, unscathed by what had happened.
And since the substitute king was killed, the omens were clearly correct there.
Indeed, of course.
This solved the mystery of the large gear at the back. It must have 223 teeth to turn the pointer of the 223-month Saros dial. The team had found something remarkable. They'd uncovered a machine that could look into the future. It could predict eclipses.
What we realized was that the ancient Greeks had built a machine to predict the future. It was an extraordinary idea that you could take scientific theories of the time and mechanize them to see what their outputs would be many decades hence. It was essentially the first time that the human race had created a computer.
The gear wheels in the mechanism programmed the computer, but where was the output data displayed? The clues were in Fragment F.
When you first start to look at the X-rays from Fragment F, there's nothing much there. And then the scales emerge as you go down through the layers. And not only scales, but you see these little scale divisions, blocks of characters here. And these look to me a little bit like Egyptian hieroglyphs, so I call them glyphs. The glyphs must be the eclipse predictions. I soon realized that the first letter here is a sigma. Sigma standing for the letter S, standing for Selene, the goddess of the moon. That must indicate a lunar eclipse. I next realized that the letter eta, H in the Greek alphabet, must stand for Helios, the sun. So this must indicate a solar eclipse. Now, what became really tough was to try and decode the next symbol, the sort of anchor-like symbol, and this took me a long time. By chance, I found a book on Greek horoscopes. Amongst a whole mass of symbols, I found this symbol in the document. It was short for the word aura, meaning hour. So what that told us was that not only did this mechanism predict eclipses, but it predicted the hour of the eclipse as well. As the hand sweeps along the scale, here it's just reaching a lunar eclipse, and here then we've got a solar eclipse in this month, followed by a lunar eclipse in that month. Our research group pooled our resources in a discussion on the internet, and Yanis Bitsakis in Athens found the phrase, "the colour is black," in the eclipse inscriptions. Alexander Jones in Toronto found this really exciting, and he then discovered the phrase, "the colour is fire red."
We were discovering a very sophisticated machine that not only was predicting eclipses decades in advance and what time of the day or night they were happening, but even the direction the shadow was going to cross and what color the eclipsed sun or moon was going to be. We're watching a total eclipse of the moon in Athens. For the ancient astronomers, eclipses had a special significance. But for most Greeks, eclipses could have a much more dire and ominous significance.
In 413 BC, a lunar eclipse led to a fatal maritime disaster for the Athenian fleet at Syracuse. Athens was engaged in a long war with Corinth and its colony Syracuse in Sicily. More than 130 Athenian triremes and 130 transport ships were blockading the harbour at Syracuse. And on the night of the 27th of August, 413 BC, there was a total lunar eclipse. Nicias, the superstitious Athenian admiral of the fleet, consulted a soothsayer on board, who said the red eclipse of the moon was a bad omen. The fleet should not put to sea for thrice times 9 days. In the ensuing battle, Nicias lost half his ships from arrows fired from the shore. The computer predicted eclipses through the Saros dial on the lower back of the mechanism. It was dependent upon gear wheels following the repeating cycles of the moon. But there was a new puzzle. The team knew that the moon moves round the Earth in an elliptical motion. That means it moves fastest when it's closest to Earth and slower when it's furthest away. How could the mechanism's designer possibly make gears that tracked this fluctuating path of the moon?
Michael Wright made an absolutely brilliant observation from his X-rays. He discovered that one of the gears at the back of the mechanism, mounted on this large 223-tooth gear, had a pin on it.
This is the pin and slot mechanism. There's a wheel in the back of the instrument. You can see with the naked eye that it's got some sort of a slot in it. The next thing you see is this round ghost in the slot. There is a pin.
Now you might think, well, they'll just turn together and that's a completely useless device. But he made this other very critical discovery. He discovered that the gear with the pin turns on a slightly different axis than the gear with the slot. So this mechanical device induces a variability in the motion of one of the gears.
And amazingly, the pin and slot device built into the mechanism plotted the variable motion of the moon.
So you get a variable motion, which I can show you best in the model. When the wheels are like this, and the pin is at the inside of the slot, the driven wheel on top is going fast. When we come round here, and the pin has moved to the outside of the slot, the driven wheel is going slow. And this is modelling the way that the moon's speed in the sky actually varies.
But when Wright originally found the pin and slot device, he failed to understand what it was for.
And he threw the idea away. It's a tragedy for him in a way that he had this absolutely the most brilliant observation in the history of the mechanism.
I didn't know what it was doing there. I even came to wonder whether it was a sort of mechanical fossil.
But there was yet another lunar complication the machine had to deal with.
The ancient astronomers were fascinated with the motions of the moon, and nothing is easy about the motion of the moon. It's very, very complicated stuff. In modern terms, we know the moon goes round in an elliptical orbit, but that ellipse isn't stationary. It rotates very slowly in a period of about 9 years. Based on cycles I knew were part of the mechanism, the Metonic and Saros cycles, I deduced the ancient Greeks had calculated this annual rate of rotation to be 0.112579655 to 9 places of decimals. I thought, well, surely the mechanism can't calculate to this degree of precision. That would be virtually impossible. I puzzled over how the designer could have possibly built gears to track the rotation of the moon's ellipse once every 9 years. In my model, I'd driven the large 223 gear that helped track the moon's movements with a 27-tooth gear. I changed Wright's 53-tooth gear to 54 teeth, exactly double the 27 of my input gear. Then I had my own eureka moment. I was on the plane to Athens. I was playing around with the figures. I knew the input gear had 27 teeth, so I put that into my calculator and calculated the result. And to my deep disappointment, it was too big. So I thought maybe it's only 26 teeth. So I put that into the calculator, and it was too small. Now, I was a mathematician, and mathematicians often have slightly crazy ideas. So I tried putting in a gear with 26.5 teeth, and I pressed the key on the calculator, and the result was 0.112579655. Exactly the right answer to 9 places of decimals. It just hit me like a thunderbolt. That twice 26.5 is 53. Michael Wright had been correct about the 53-tooth gear. The riddle of the 53-tooth gear had been solved at last. It turns the large 223 gear with just the right 9-year rotation, so that the pin and slot exactly models the ancient Greek theory of the moon's variable motion. We'd followed the trail of clues in the prime numbers, the numbers 19, 127, 223, and then finally 53, to understand how the mechanism worked. And it was just an amazing moment when everything came together. We knew now what all the numbers in the tooth counts were, which had been a complete mystery before and not understood. And it was just a quite incredible moment.
The team's next quest, however, was just as formidable. Who'd invented this extraordinary machine 2,000 years ago? This investigation would throw up many more surprises.
We thought the answer to the question who made the mechanism might lie inside the mechanism itself.
Tony Freeth in London and Alexander Jones on the other side of the Atlantic were deciphering Greek month names on the Metonic upper back spiral. Then the breakthrough happened.
Every Greek state had its own distinctive calendar. 4 of the month names stood out as being really quite rare. There was one called Lanotropios, another Dodecatius, a third called Pseudrius, and a 4th one called Phoenikaios, which was the first month of the calendar. I realized that these 4 months belonged to the calendar of ancient Corinth, and so they had to be coming from either Corinth itself or from one of the colonies that Corinth had founded, for example, Syracuse over the sea in Sicily.
There were more tiny clues, which might point towards a Corinthian designer of the mechanism. I was looking in the X-rays at this little subsidiary dial that's divided into 4 sectors, I noticed this word Nemea, and I had no idea what it meant. Almost immediately, Alexander Jones in Toronto emailed me with the answer. Now you have a clear reading Nemea, which I'm darn sure is indicating a year when the Nemean Games were held. This was one of the 4 Pan-Hellenic Games. The Nemean Games, I discovered, took place every 2 years and were originally based on warlike events. Only warriors and their sons could take part. We were curious as to why one of ancient Greece's famous Pan-Hellenic Games should appear on the mechanism, and how would this lead us to the designer?
These are the starting blocks where the athletes began their races going down the track. They would put their feet, their bare feet, mind you, in the grooves, one foot in the rear groove, one foot in the front groove. They would try to get their weight to move out just as the race began. There were the standard running events. One stadion in length was the premier event of roughly our 200-meter race. There was a race in armor, a double stadium race, where the athletes wore helmets and shields. There was the Pancratium, where people broke arms and strangled one another. Really lovely event. The Nemean Games were on a par with the games at Olympia, Delphi, and Isthmia. Those 4 sites were the crown sites.
On this small dial, we found 4 sectors in the Nemean Games, the Pythian Games at Delphi, the Isthmian Games at Corinth, and finally, the most prestigious games of them all, the Games at Olympia, that happen every 4 years.
The Olympic Games were believed to have been founded as early as 776 BC. This stadium held 45,000 people. We began to wonder why there had to be a dial on the mechanism showing the dates of these Pan-Hellenic Games, like the Olympics, events that took place at such regular and simple intervals, every 2 and every 4 years, numbers they could count too easily on their fingers. The Games could therefore have offered a fixed reference for the 19-year dial on the mechanism, a fixed date transcending the rise and fall of Greek states and their magistrates and the deaths of their kings.
The surprising thing about this dial was the size of the lettering for the Isthmian Games at Corinth, far bigger than the prestigious Games at Olympia, as if the Corinthian Games were much more important.
All the evidence now suggested that the mechanism's designer came from Corinth. But the team believed that it might have originated from Corinth's rich colony of Syracuse in Sicily. In the 3rd and 4th century BC, Syracuse was the 2nd largest city-state in the entire Greek world, founded centuries before by poor Corinthian immigrants from the Greek mainland. It had prospered remarkably.
Significantly, Syracuse was the home of the most brilliant of all the Greek mathematicians and engineers, Archimedes.
As an astronomer, Archimedes determined the distance to the moon. As a mathematician, he showed how to calculate the volume of a sphere and how to calculate that fundamental number pi.
We believe that only a mathematician of Archimedes' status could have designed the Antikythera mechanism. As a brilliant inventor, he designed screw devices to lift water, and he designed machines with grappling hooks that could grab enemy ships out of the water.
Archimedes lived in Syracuse in the 3rd century BC. At that time, Rome was challenging the power of Greek cities in southern Italy. If rich Syracuse could be taken, all of Sicily would come under Roman control. Led by the Roman general Marcus Claudius Marcellus, Roman legions laid siege to Syracuse in 214 BC. Archimedes is believed to have designed cranes to pull Roman ships out of the water. Then, after 2 years of siege, by trickery, Roman soldiers got inside the city. General Marcellus gave orders that the city should be sacked, but Archimedes' life be spared. But according to the historian Plutarch, a Roman soldier came upon an old man drawing circles in the dust. When he refused to obey an order, the legionnaire ran Archimedes through with his sword. Syracuse was stripped and its treasures taken to Rome. Just 2 valuable objects were personally taken by General Marcellus. He states they were machines belonging to Archimedes. These, the team believe, might be early versions of the Antikythera mechanism. 150 years later in Rome, the formidable orator and consul Cicero writes of a sighting of one of Archimedes' machines in the house of Marcus Marcellus, grandson of the victorious General Marcellus. Cicero writes,
Archimedes had thought out a way to represent accurately by a single device those various and divergent movements of the 5 planets with their different rates of speed. Thus the same eclipse of the sun would happen on the globe as it would actually happen.
Were the rotating planets Cicero wrote about 2,000 years ago the final clues to the construction of the mechanism? Could Michael Wright's complex planetarium on the front of the mechanism be simplified to match the design genius of the original?
I'm going to start off just by passing around some pretty pictures, and then I'll explain why I'm passing them. These are medieval pictures showing the cosmos, but the way that it's shown is an ancient Greek way. What you have is the Earth at the center, and you have a set of rings which are supposed to be spherical shells in which each of the planets going from the moon out to Saturn are. The front display must have been a picture like these medieval ones that showed the cosmos in cross-section. This is a picture that I did from the tomography. It's composite from several different layers so that we get a big chunk of the back cover inscription all together. And the part that I'm passing around is describing the planets. Venus's name is there, but probably all 5 are there. And they are in the order that these pictures show, going from the moon and then Mercury, Venus, in the order going away from the Earth to the stars. And then right after that, you get a line that says, and beside the cosmos is, and the text cuts off. Now, my idea about this is that the front display must have been a picture like these medieval ones that showed the cosmos in cross-section.
Now, I began to think, how can you mechanize these planets so it exactly predicts their positions in a way that's simple and not over-complex? Mars is what I started with. You'll notice it's got 4 gears, it's got a pin in the slot, and it looks, in principle, almost identical to the moon mechanism. That's Mars. This is Jupiter. Very similar, 4 gears, pin in the slot, exactly the same sort of thing. And this is Saturn, which, at a quick glance, you might think is the moon mechanism. It looks identical. Moon goes around once a month, Saturn goes around once every 30 years. And you finally end up with all the planetary mechanisms in here. I was just amazed. They all fit to create the cosmos on the Antikythera mechanism. Just like on Michael Wright's planetarium model, but much, much simpler. That coincides exactly with Alex's picture of the cosmos. I'd love to take credit for discovering these things, but I think I was rediscovering what the ancient Greeks did.
But all this leaves a major unanswered question. What happened to the brilliant Greek technology that produced the world's first computer? Why was it never developed? Why was it lost from the Western world?
As first the Greek world declined, followed by the collapse of the Roman Empire, historians believe Greek scientific texts were passed east. By the 4th century AD, information on the mechanism perhaps went first to the Byzantine world, and then to Arab scholars. Michael Wright has a clue suggesting some of the mechanism's Greek technology would later become available to Islamic science.
In 1983, a man came into the museum. He was a collector of astrolabes. He bought this from a dealer, we think, in the Lebanon. We believe we can date this instrument to about 520 AD. That makes it the 2nd oldest geared instrument that we know of after the Antikythera mechanism. The gears in the back connect to this wheel, which shows the phase of the moon. That's new moon, the waxing crescent.
So it's likely that the ancient Greek knowledge of gearing was kept alive in the Byzantine world and then by the Arabs. It was reintroduced into Europe in the 13th century when the Arab Moors came up through Spain.
Then, during the Renaissance in the 14th century, highly sophisticated gear trains suddenly appeared in clocks all over Central Europe. They all used the complex gears found in the Antikythera mechanism. The original mechanisms coming from Archimedes' workshop are likely to have been much larger. But as the Greek engineers grew more confident, over several generations they were able to minimize their technology and bring it down to the size of a box. And that box was almost certainly the most prized object on the Antikythera treasure ship.
The Antikythera mechanism was small, light and portable. They'd managed to cram nearly all their knowledge of astronomy into this small geared device. It was the theory of almost everything in a box, very similar to today's modern laptop computer.
Here, we believe, is the complete and intricate machine. On its rear face, Greek scientists of 2,000 years ago fashioned a computer mechanism that displayed a calendar that followed the moon, that predicted eclipses, while on the front, they reproduced the universe as they understood it, with the 5 planets, the sun and the moon, performing the complicated steps of their dance through the heavens. Here was Greek genius at its height. The great and divine cosmos represented through mechanism by scientists who wished to show that there was no mathematical challenge beyond their abilities.
We know that this society was the birthplace of the art, architecture and culture that is the foundation of our modern world. Now we also know that it was the cradle of advanced technology. Derek de Solla Price, who pioneered the early research on the mechanism, said this: "It's a bit frightening to know that just before the fall of their great civilization, the ancient Greeks had come so close to our own age, not only in their thought, but also in their scientific technology."
But if it hadn't been for 2 storms in the Mediterranean, we might never have known about this mechanical wonder. The first storm, around 70 BC, sunk an overloaded Roman trading ship carrying the precious mechanism. Then, in 1900, another storm drove a team of sponge divers to shelter off the island of Antikythera. Without these 2 events, the most important scientific discovery to emerge from ancient Greece might have been lost forever.